Hi, I am Apekshik. I have picked a topic that has fascinated me since I first learnt it from my dad this summer. You know what it is? It's the Fourier Transform. This is very interesting because it unravels the mysteries of nature and it's omnipresent. I have attempted to create this video by stitching those discrete images that were popping into my head during those discussions. I hope you enjoy the video as much as I have enjoyed making it. So let's start and try to decode it. Like all other complex concepts, this one too has a simple idea behind it. The motivation behind Fourier's technique was to be able to make or break functions like vectors. The question was whether we can combine simple functions like vectors in order to get more complex ones. Similarly, can we break a function into its components like we break down a vector when we decompose it? So, in a nutshell, the Fourier transform is all about making and breaking of functions. We shall try to discuss how it is so. Okay, let's start with the simple situation, that is, when our function is a repetitive one. But why this kind of a function? Because all functions can be classified either as a repetitive one or a non-repetitive one. They complete the set. If we find the trick for both, then we're done. So let's get back to a repetitive function. Suppose we have a repetitive function in time, like this. Fourier thought that if there might be a way to build this function from some simpler functions, they better be repetitive. This is natural, isn't it? Now, repetitive functions can be of many types, like this, or maybe this. But observe that the first two are having a very bad nature of suddenly changing their moods. On the other hand, what about the third sinusoidal function? Let's see. If we rotate a stick in a circle and track the shadow of this stick on a vertical wall, we will get sinusoidal functions like this. See, this function doesn't change its mood suddenly. It's continuous, it's smooth, and it's beautiful. This function has another beautiful property. Look, if we start tracking this rotating stick after it has already covered a certain angle phi, the curve will look something like this. But the beauty is, this too is periodic. Now, if we make the starting angle phi to be 90 degrees, we get a curve like this, and this is our cosine curve. So, sine and cosine functions are just shifted versions of each other. So far, so good. So now onwards, let's take this cosine as our main curve to build our repetitive test function. Now the most important point is that the stick has to rotate at a certain speed omega in order to complete one revolution during one period of repetition. Otherwise, even if the cosine or shifted cosine is repetitive, either it will lag behind or overshoot the period of the original repetitive test function. Let's follow a stick which rotates at 15 revolutions per minute, that is, it completes one revolution in 4 seconds. Suppose our test function has same time period of 4 seconds. Now if we rotate the stick faster than this, the cosine function gets squeezed and it gets stretched if the stick rotates slower. But see, they do not fit the period of our test function. But wait, what if it rotates at double the speed, that is at 30 rpm? Yes, it fits into the period, but now we have two of our cosine curves. We call this the squeezed cosine. Now let's take a base cosine and a squeezed cosine and combine them. See, the combined curve also repeats itself after a period t of our test function, that is 4 seconds. But wait, let's see what happens if we take different amounts from both of these and combine them together. Let's take a 1 amount from base cosine and a 2 amount from the squeezed one. See now that the length of the sticks changed, but if we combine them together, the combined curve again repeats itself after time t. One more thing, now both the sticks can also start at different angles but the period remains same. We call them shifted cosines. Now if we add the horizontal shadows of these shifted cosines and watch at different times, it matches with our repetitive test function. Our job is done. This was the story of two rotating sticks. Now we can take any number of sticks and combine them. The only thing is that each subsequent stick rotates at a speed that is more by omega than its predecessor. That is 3 omega, 4 omega, etc. Now we see that base cosines, squeezed cosines or shifted cosines can be combined to get a complex curve like our test function. This story was written in shorthand by Fourier like this. It is important to note that f of t is a repetitive function of period t and omega is the base frequency corresponding to that period. Note that when n equals to 0 in the formula, it represents a constant value which takes the whole function up or down like this. All these things can be represented in a pictorial way with this 3D construction. The ft plane is used to represent the repetitive function. Another axis perpendicular to this plane can be imagined to represent the omega axis. This can be imagined to be carrying a rotating sticks. The nearer the stick to the origin, the slower it rotates. The first stick rotates at the base omega. That means it completes a full rotation within the time period t of a repetitive function. The second one rotates with double the speed. The third one rotates at triple the speed of the first one, and so on. That means the distance between them is omega. Now we can stretch our imagination a little bit and convert the sticks into plates of length omega, and going a step more, we can imagine these plates to be embedded in some transparent drums. So, what do all these things represent? The drums represent the smooth repeating functions contributing to the test function. The radius of each drum represents the amount each function contributes, and the initial orientation of each plate inside the drums represents the amount by which the functions are shifted. Their locations represent by how many times the functions are squeezed. Now, when we look from the negative time axis, we can see that the upper half looks like combining different functions to get the test function. Let's investigate another thing. Now suppose the time period of the test function is small, then the first drum which represents its base speed will rotate faster since it will come to its original position in less time. That means the drum widths which represent the base speed will be larger. Conversely, if the time period of the test function is larger, the drum widths will be smaller. The second drum will also come closer but still rotating at double the speed of the first one. Similarly, the third drums and the others. Now comes the best part of the argument. Just imagine that the period of our test function is very large, almost infinite. Does it not represent an arbitrary non-repeating function, the other exclusive part of repeating functions? Now see what happens to the first drum. What will be the speed of its rotation? Will it not be hardly rotating? Because it should take almost infinite time to complete one full rotation. What it means is that the speed is almost zero. Then what does it say about its location on the frequency axis? It will be infinitesimally close to the origin. Now what will be the length of the drum? Yes, it will be infinitesimally small, almost of zero length. Where will be the second drum located? Infinitesimally close to the first drum. Then all the drums which have almost become thin circular plates will fill the omega axis. If we look from the negative time axis, it will look something like this. In a rough way, this is the Fourier transform for our non-repetitive functions. So we can say that what Fourier series is to repetitive functions, Fourier transform is to non-repetitive functions. Now why did I say in a rough way? Let's see. This has something to do with the energy content of our test wave. When it is repetitive, it is broken into so many cosine waves that the total energy is the sum of each of these discrete waves. These energies are proportional to the square of the amplitudes of the waves, or in other words, to the square of the drum radius. But when the wave becomes non-repetitive, the drums become very thin, almost continuous in a sense. Then the question of energy per drum makes no sense as the width of each drum becomes zero. For example, if we ask for the mass at a given point in a continuous body, it is zero. But the whole body has got a mass. To overcome this problem, the density function has been defined for a continuous body, and in a similar way, the Fourier coefficients represent the density of the drum radius in our case. So instead of energy at a given omega, we talk about energy within certain delta omega. Now we can write it like this. So we can now represent any type of function, be it repetitive or non-repetitive, in simpler forms using this transform. Fourier transform has got numerous applications in nature. It's being used by your MP3 player every time you hear a song, or when your ear uses it to give information to your brain like it's doing it right now. It's just another mystery unraveled by Fourier.